Out there, the absolute zero-margin vacuum of deep space is a hostile environment, actively unmaking biology upon exposure. Looking at the lunar surface, the baseline reality becomes entirely clear. There is near absolute vacuum and constant heavy surface radiation. Mars introduces even tighter constraints, a thin, toxic carbon dioxide atmosphere, and a communication latency with Earth that averages up to 13 minutes each way. These parameters completely eliminate the option of Earth-style resource extraction. They also remove any possibility of real-time technical intervention from mission control during an emergency. This creates a strict engineering mandate. Any habitat placed on these bodies must be completely sealed, totally self-reliant, and possess zero margin for structural or systemic error. We cannot launch a habitat of that complexity and simply hope it functions upon arrival. We must prove the architecture under extreme, isolated stress here on Earth first. To survive the lethal realities of space tomorrow, we have to perfectly simulate their extreme physical and psychological constraints today. This is achieved through analog missions, isolated terrestrial environments specifically selected for their extreme weather, geographic remoteness, or geological similarity to target planets. Desert habitats, like the Mars Desert Research Station in Utah, replicate the precise geological terrain required to test extravehicular activities in a confined landscape. Underwater analogs, like the NEEMO project, force crews to operate under continuous pressure, mimicking microgravity isolation and creating absolute dependence on mechanical life support. While these analogs are highly effective at testing human psychological resilience and basic hardware durability, the physical structures themselves are often just isolated empty shells. Designing the complex integration of life-sustaining subsystems inside that shell is the objective of an analog. Erecting a pressurized tent in a desert yields zero scientific value unless its internal life support architecture is rigorously engineered to function as a closed-loop system. The most critical component of this habitat is the Environmental Control and Life Support System, or ECLSS. This system must operate continuously without drawing on external atmospheric or aqueous resources. This diagram shows the regenerative loop. Waste from one process becomes fuel for another. The system captures exhaled carbon dioxide, converting it directly into breathable oxygen. Simultaneously, internal systems generate immense heat, which must be expelled through external radiators to prevent systemic meltdown. These connections are highly interdependent. A minor fault in thermal routing causes the air scrubbers to overheat, which can lead to a rapid loss of breathable oxygen for the crew. In physical reality, these systems are densely packed. Kilometers of fluid lines, pumps, and wiring share a single, highly confined rack. Attempting to design this level of interconnected complexity using traditional static engineering documents, like disconnected PDFs and spreadsheets, is dangerously inefficient. In a document-centric workflow, updating a power requirement in one spreadsheet rarely updates the corresponding thermal document. When a single overlooked variable dictates whether the crew survives, relying on static, disconnected documentation introduces a fatal liability. To manage this extreme complexity, modern aerospace engineering utilizes model-based systems engineering, or MBSE. Instead of writing thousands of separate documents, engineers build a single, dynamic digital database where every component is linked mathematically. Using specialized software tools like Capella, teams map the exact relational networks of power, mass, and data flowing across the entire habitat. However, a software tool cannot organize a system on its own. It requires a rigorous logical framework. This is where the Arcadia methodology is applied. Arcadia enforces a strict structural philosophy. Engineers must precisely define why a system is needed before they are permitted to decide what physical hardware will fulfill that need. MBSE and the Arcadia framework work together to transform the analog habitat from a static physical structure into a fully computable, testable web of logic, eliminating design blind spots. This diagram illustrates the Arcadia framework, divided into 3 key layers. We begin at the top with operational analysis. This layer defines the entities, the astronauts or researchers, and outlines their required capabilities, such as sleeping, conducting experiments, or executing EVAs. From there, the framework moves down to system analysis. Here, human needs are translated directly into system functions. The operational need for the crew to breathe dictates the system function of managing oxygen inputs and carbon dioxide outputs. Finally, the design descends to logical analysis. This layer dictates exactly how the system will achieve its functions. Behaviors are grouped into logical components, mapping the fluid and data paths without committing to a specific brand or model of hardware. This tiered approach guarantees absolute traceability. Every logical component at the base of the framework traces directly back up to the specific operational need that justifies its mass and power consumption. By completing this architecture, engineers construct and verify a complete digital twin of the mission's logic before the first piece of hardware is ever manufactured. The value of the Arcadia model lies in its capacity for destruction. It allows engineers to aggressively test the habitat's resilience against failure. Take a sudden anomaly scenario. A severe dust storm sweeps over the site, coating the solar arrays and instantly dropping power generation by 40%. Fed into the MBSE model, the system reacts immediately, tracing the failure cascade to highlight every subsystem starved for power. It tracks this deficit up to the operational layer, calculating exactly how many hours the crew has before life support critically degrades. Engineers utilize this rapid feedback loop to iteratively patch the architecture. They introduce modular battery redundancies and reroute thermal flows months prior to the physical construction phase. The extreme analog habitats deployed in the deserts and oceans of Earth are the physical execution of these exact digital models. Space exploration relies on the rigorous management of extreme systemic complexity. These terrestrial analogs, driven entirely by rigorous systems engineering, provide the definitive testing ground required to survive the harsh realities of the Moon and Mars.